The other algorithm that we can use to find such a minimum spanning tree is Kruskal's algorithm. And it is similar, but a bit different. So instead of maintaining one cluster, we're now maintaining a partition of clusters. So we're partitioning the vertices into different clusters. And initially each vertex forms a single cluster. And so the idea of the partition is that each vertex is always in exactly one cluster. So each vertex is in a cluster, and each vertex is in a cluster at most once. And each cluster contains a minimum spanning tree of all the vertices in that cluster. Now, what we're going to do is we're going to pick the edge with the smallest weight that's not part of a minimum spanning tree yet. So an edge that connects different clusters. So initially we're gonna, if they are indeed different clusters, then we are merging both clusters by adding the edge to our minimum spanning tree. And if both of the vertices were in the same cluster, then remove the edge so that we are not getting that edge again. And then repeat this until we have a single cluster with a single minimum spanning tree. So again, those weights, we're going to use a priority queue to constantly find the smallest weight. So let's look at the same graph again. So initially, all vertices are its own cluster. And we're now going to find the minimum edge. So that's this one edge. And we're going to join those two clusters. Now again, we're finding the minimum edge, which is this one. We're going to join those two clusters. Now again, we're finding a minimum edge. And we have three choices, doesn't really matter, but let's pick this one. We're going to join this cluster AB with the cluster D. Now again, 3 is the minimum, so we're going to join this cluster ABD with the cluster CE. Now the minimum that doesn't belong to a cluster yet is this edge, but E and B already are in the same cluster, so instead we remove the edge. Then we're finding 4, and again B and C are in the same cluster, so we remove the edge. Then we're finding 5, which does the same, we remove the edge. Then we're finding 7, F is a new cluster, so we add the edge. For 8, we remove the edge, and for 9, we add the edge. And then we find again the minimum spanning tree. Note that we got the same spanning tree, just added in a different order. And also note that we could have gotten a different spanning tree. For example, if you wouldn't have this edge, but this edge instead, this would still be a spanning tree with the same weight. So what data structure do we need for Kruskal's algorithm? So as you saw, we needed the priority queue, but we also needed this thing which is called a partition. And this is a partition of clusters. So let's have a look how that would look in code. So this could look like this. This is a simple interface of a partition with the following 3 methods. So it can make a cluster starting with an element, E in this case. What it can also do is find the leader of a cluster. So in this implementation that you can also see in the book, it assigns a leader to each of the clusters. So one of the vertices in the cluster is the leader. And here, given some vertex, we're going to find the leader. And this is used to make sure that two things are the same cluster, for example. If both have the same leader, then they're the same cluster. And then the last method that needs in this partition is to make a union of two clusters. Because of course, that's what we're constantly doing, right? We're constantly making a union of two clusters when adding an extra edge. So we make a union of the clusters with vertex P and vertex Q.